Good morning, everyone. Okay, let me share my screen. So, okay, I hope this is visible. And as I said that all of you are have rights to unmute and speak or put forward your queries if you have. Okay, so let me briefly review that what we were doing in last lecture. Right. So we were basically calculating or looking for the expression for a number of microstate accessible to a system in a macro state defined by these three parameters: the number of particles, the volume accessible to the system, and energy uh, available to the system, right? So these parameters need to be defined precisely to define the macro state. Then we looked upon that what are the features of this number of microstate function is, and then I told you once you have the expression for this, and today we will be applying this knowledge for an ideal classical gas, right? I should not say classical gas, although it's a just ideal gas situation, right? So we'll in explicitly evaluate this function under certain assumption for the ideal gas case. Okay. So as I discussed last times, once you have the expression for a number of microstates for a given macrostate, then you can straightforwardly write the expression for entropy via this statistic and thermodynamic relation as proposed by Boltzmann. S is equal to K log omega, and then from this basically we can derive all the thermodynamical parameters almost straightforwardly. This is just mathematics, no physics going behind or logics are going behind this. It is just a straightforward differentiation to calculate, for example, temperature, pressure, chemical potential, and so on. Right. So we can. I also discussed that we can invert the expression for entropy as a function of energy, which is here because this omega is function of energy as well as volume and number of particles also. But this can be inverted in principle so that I can write my energy as a function of entropy, volume, and number. So then having this particular expression, I can directly calculate the pressure, chemical potential, and temperature using this first of thermodynamics, like we discussed last time. So this was kind of a scenario we were discussing in last lecture. So today, yeah, and also I think by the end of lecture, I showed you that once you have all those S, T, P, and mu with you, you can further calculate these thermodynamical parameters: Helmholtz free energy, Gibbs free energy, enthalpy, right? Heat capacities at constant volume as well as constant pressures. So this is straightforward. Let's try to see if we can apply this to a physical system, right? So any question till now, if you have? Okay. So I'm basically interested in talking about this. So the ideal classical gas, and yeah, of course, this is, as I said, this is going to be an application of the understanding what we have developed till now that we will see today. And it may be yeah, it is bit mathematical, right? But I have planned to wind up this example today, as of today itself, right? So I don't want to extend this because we have many things lined up to be discussed. So yeah, so the idea is that my ideal gas, I have certain assumption that my ideal gas is monatomic, so that there is no internal degree of freedom going on. So there is no rotational or vibrational degrees of freedom are involved as of now, and all those individual particles or atoms are basically not non-interacting. This you can say a high temperature, low density kind of limit, right? So high temperature and low density. So low density means the particle are far away from each other and they actually don't interact with each other. So even the real gas is going to follow these assumptions which we are going to assume here, right? So yeah, So now what's the target? What we have at our hand? So idea is, our goal of this whole discussion is, can we find the number of microstates accessible to such a system of monatomic classical non-interacting gas molecules, the system composed by such molecules, defined defining a number of course, gas molecules, how many gas molecules are there, volume of the gas, as well as energy, precise description of the energy. Although this is very ideal situation that can you can precisely define the energy, this is not a very realistic, you can say, scenario, because in reality you may define your energy below certain a threshold. So all the energy can be energies can be possible, or you can say that the energy may have certain window, that energy, we allow energy to vary between some delta plus minus range. This could be more realistic situation. This will see once we will evaluate this number of microstate for this macrostate, then we will basically shift to this scenario also. So it's not very hard. Okay, so before even going or jumping into actual calculations, one quick observation I want to share with you is, although I written here, it is written here in a bit detail, but the idea is, you might remember. Let's not means see this slide for timing. Just try to listen to me. Okay, so the idea is, you might remember in your, I think, graduation, you have studied distribution of, for example, four particle in two boxes, right? So this kind of you can say distribution you studied when you started your undergrad statistical physics and thermodynamics course. So my idea was, so how many number of possible ways are there if you have, suppose, n particle, and you want to distribute those n particle amongst two boxes, for example. Let's take n balls in two boxes, right? So the idea, you can quickly see that number of possible ways are 2 raised to power n. For example, if you have one ball and you want to distribute in two boxes, there are only two ways. You can put that ball in box number one, or other possibility could be you can put that ball in box number two. So these are the two possibilities. So you can say this is 2 raised to power 1, because there is only one particle. Now if you switch to two particles, right? So let me see how many number of microstates basically are available. I already know what is going to happen. That's why I'm drawing like this. So what you can do is, just give me 1 minute. Hmm, just 1 sec. Okay, so if this is my box number one, this is box number two, and I have two particles now. So you can put both of them here, nothing here. Or you can put this guy here and this guy here. Or this could be another situation, or this could be a fourth configuration. You can't have more than this. Okay, so this is basically 2 raised to power 2 possibilities. Similarly, if you take three particles, you are going to get 8 ways, which is 2 raised to power 3. If you have n particle in general, so you have 2 raised to power n configurations, right? Basically, for, and what is number two sets signifying here? It is, you can like take the correspondence of this number 2 with the volume available to the particles, right? So if there is one particle, the number of possible ways in which one particle can uh, be put or take positions in volume of space occupied by volume V, then those number of ways are basically proportional to this volume. So if I have two particles, for example, now if my n is equals to 2, then the number of possible ways in which these two particles can occupy volume V is proportional to V square, similar as it is going here, 2 raised to power n, right? So if there are suppose n particles, then the number of possible ways, they will be proportional to V raised to power n, basically, right? So this is a observation, or a quite I would say logical argument, that these number of states has V dependency, but for n such particles, this number will be proportional to volume raised to power n. And of course, I'm assuming here that these particles are not interacting with each other. and they are not constrained that we are putting. So in principle, we can put two particle exactly at same place in volume V, right? This may sound absurd, but this is a part of assumption. Okay. So having said this, so what I can get out of this? So if I assume that this is going to be proportional to this thing, so my idea is, okay, so now we know this, that my entropy is linked to number of microstates like this. And we also defined our eta parameter while we were discussing the equilibrium of two subsystem brought into thermal contact, as well as a penetrable wall, as well as movable wall. So we defined this parameter eta, which was pressure by temperature. It's a partial differentiation of this entropy function with respect to volume at constant number of particle and energy. So this was something we discussed earlier also, right? So but if you see that S looks something like this, so if you put it here, so you will get expression for this pressure by temperature like this. So it's just taking this K out and keeping log omega inside, right? So n and E constant. Now as I we just asserted in last slide, that my this omega number, the number of microstates available to n particles occupying volume V, is proportional to V raised to power n. So my this is nothing. So this differential will be equal to n by V, right? Satisfy yourself that how it will come equal to n by V. Okay, so you can change this proportionality into equality, and then you can put upon constant of proportionality some alpha kind of thing, maybe beta, doesn't matter, right? So then put that omega here and then do this differentiation. You will see that this is equal to n by V, and you see this was originally p by t expression. It means my p by t is going to be just k n by V, right? So where k came from this equation, the Boltzmann constant. And if you assume that your gas has n number of moles, and then you can write total number of particles as number of moles time Avogadro number, because this is the number of particles per mole, right? So which is 6.02 10 is to power 23 uh, per mole. So it means you can replace this guy there, and this can be rearranged, and I think you can see where we are leading up to. So we can so straightforwardly drive the ideal gas law, right? So I think you must appreciate that we have not gone into the any detail analysis, but still we were able to generate this equation, right? Only with this assumption that my omega is going to be proportional to V raised to power n. That's it. This is generating this thing, right? So, and of course this k times Avogadro number is what we call gas constant per mole. So this R, the values are available on standard textbooks. Okay, so any question till now? I would like to would love to answer. If you have, you can type in, otherwise I will move ahead. Okay. Okay, so now let's get into more detail of evaluating this number, which is, let me take different color so that, okay. So I'm now interested in evaluating this more explicitly. Basically, I want to see the feature of this omega for this ideal gas situation. Okay, and basically I'm interested how it depends upon basically number of particles, the volume. Although I said that this will be proportional to V power n, right? But we will see that how it comes into the existence. And of course, it will depend upon energy. Okay, and also in order to evaluate this number, these conditions has to be satisfied. Okay, so you can't like vary this energy parameter arbitrarily. It has to satisfy these conditions, as well as the number of particle constraints, as total number of particles of the system is a constant number. So now I'm just considering one expression for energy eigenvalues of a single particle. I should have that written somewhere. Consider a particle. It's a single particle. Do remember it, these are not n particle right of now. So it's a discussion which I'm going to start from this point. Okay, so it's a single particle and the energy eigenvalues for such a single particle confined to a cubical box. So suppose I have a cubical box, kind of this thing, right? And each side of this box is L. So of course you can see that volume is going to be L cube. So the energy eigenvalues, you derived this in your lower class also. It's this H is Planck's constant divided by ml square, nx square, ny square, and nz square, where these quantum numbers can only take positive integer values, right? You must know this. You must remember this, that they are going to take only integral positive values. Okay, so yeah. So the idea is here that this h is Planck's constant, m is mass of the particle, and l is of course length. And you can very easily see that l square is basically v raised to power 2 by 3. This is not very hard to observe. This can come from here also. Okay, so my idea is that this energy depends upon volume, right? So if you remember, I told you this thing that volume enters into the expression for number of microstates via energy. Okay, that's why we write this n, v, and e. So this dependence of this number of microstate directly upon n and e, it is basically obvious from these two conditions, right? But these two conditions don't involve volume. But now you can see that energy eigenvalue, basically they have volume somewhere inbuilt in it. Okay, so I'm just rearranging this equation number 5 to write nx square, ny square, nz square equals to this number, and I'm just scaling this energy eigenvalue as E star, so that you can like absorb all these constants for 8m, as well as the uh, this volume, which is a kind of constant by a Planck constant, into the energy equation. So this is just a rescaling thing. Okay, so now of course these nx yz, if we can make a kind of table thing, nx ny nz, right? So all of them can be 1, so 2 can be 1, this can be 2, or this can be like this, or 2 1 1, then 2 guys can be 2. So these permutations can continue, and like you can write as many as you want, right? But my point is that these values are going to decide that which, these are basically various microstates available to this system for single particle, because I'm writing the energy for single particle. As I just said above, it's the energy eigenvalues for a particle, not n particle as of now. Okay, so that's why if you see I'm representing this thing, because these are going to provide me various number of microstates, or omega is going to basically proportional to this number. Now omega is going to be a function of this, or instead this whole expression is kind of omega for single particle. That's why I wrote omega instead of n. I'm writing 1. Of course energy is E and volume is occupied by V. Okay, so for single particle, of course I have 3 degrees of freedom, you know, along xyz. That's why only 3 numbers are coming, nx, ny, and nz. But suppose if I have n particle, n such particle, then I will have 3 n degrees of freedom, right? So instead of running this index only for 1, 2, and 3, I can write the general expression for similar to equation number 6. Now for my total n particles, like this. Just give me 1 sec. Let me switch the slide. Yeah, so you must agree this is just a generalization of same result, right? So my this nr running from 1 to 3n, the number of degree of freedoms. So this nr square is just when earlier we had nx square plus ny square plus nz square, those were only even 3 degrees of freedom for one particle. Now we have n particles, 3n degrees of freedom, so this summation can be extended, or that result can be generalized like this, right? And you see I replaced that small e, which was the energy for single particle, with capital E, which is basically energy accessible to all 3n particle distributed over volume V. So this is something you can see we can have this result. Now before going ahead with this equation number 7, I have a small discussion which we can immediately see, because I just said that this omega is going to be proportional to how many various number of states are accessible to my quantum, my system. I should not say quantum, sorry. So that is going to be decided by how many various permutations I have over nr. Nr is like n1, n2, n3, and so on. This will go up to n 3n, right? So these, they can take value 1 2 3 4 so on. Okay, so different permutations are there. So all those different states are basically total number of microstates available to system. So this omega depends upon this thing, and one thing you can see very quickly, that this volume energy is coming like this. It means that if I'm writing my omega as a function of n, v and e, the energy volume term will appear like this. So this is again one straightforward result which we can see just from equation number 7, that whenever this energy and volume are going to appear in the expression for number of microstate for this ideal gas case, this energy volume are going to appear like this, right? Now let's take advantage of this functionality, because if we get some loophole, we can always take the advantage of that thing. Okay, this is something like conservation of momentum when you studied your collisions. Suppose in one dimension or in two dimension in your 10 plus 1 or 10 plus 1, I think, right? So if you have some conservation law that you know that total initial momentum vector will remain equals to total final momentum vector, then you utilize that you can say constraint to do some calculation, so that you knowing initial velocities of the incoming particle, you can predict the velocities of the outgoing particle and so forth, right? So similarly, now we have this tool with us, so let's see if we can utilize this to derive certain property of the ideal gas, right? Now I am looking at this very special case, the reversible adiabatic case. For reversible, I mean to say there is no heat entering. For adiabatic, I mean to say that there is no heat entering or leaving the system. So dq is 0, because dq is also tds, so it means my entropy of the system is a constant. And entropy, if I'm fixing, and if I'm fixing suppose a number of particles of the system 2, then from this expression, if n is constant, uh, I would say entropy is constant, which is basically k log omega. So it means this number is going to be a constant. So it means if this is constant, n is constant, it means v raised to power 2 by 3 into e is going to be a constant, right? So this is just a simple argument. So if this number is a constant, means this is one of the condition that ideal gas is going to satisfy always. So we just saw earlier that pressure we can write something like this. This is a result from thermodynamics. And if you use this condition, take this constant, any constant, then take this v2 by 3 downstairs, then differentiate this e with respect to v at constant n and s, you are going to get this relation. It means pressure of an ideal gas is always 2/3 of the energy density of the gas, right? And let me tell you, this result is quite universal. It doesn't matter you consider quantum mechanical scenario or classical scenario or classical ideal gas, quantum mechanical ideal gas. So this result is going to be followed, because we have not gone into detail or any detailed internal degree of freedom or configuration, right? So it means this result is quite general, and you will see that this result is going to come again and again. Okay, so yeah, that's what I'm saying here. And of course, if you can see that I wrote this thing as a constant, so you can put this thing back here. Okay, how I did is, so my energy from equation number 10 can be written like this. So if I use 10, but equation number 9 says that v raised to power 2 by 3 into e is constant. So if I feed this e here, okay, so then it will give me that p v raised to power 5 by 3 is going to be a constant. This is another property we can drive straightforward. Okay, so yeah, any question till now? I would like to answer. Okay, so if no, let's move a bit ahead. Okay, so now this is something important. Okay, now again, we have not yet evaluated this number. We just saw that that okay, we have argued a couple of things. That one is that my omega going to be proportional to the volume raised to power n. This is one argument we gave, and from this we quickly derived the ideal gas equation, right? And then in second argument, we saw that omega as a function of n v e, that this v and e are going to appear in certain fashion only. So this is n separately. So this e v raised to power 2 by 3, right? So they are going to appear like this always, right? And from this we derived certain more conditions that pressure is going to be two-thirds of energy density, then P a couple of things we had on this page, that is E into V raised to power 2 by 3 is going to be a constant for gas, then P V raised to power 5 by 3 is going to be a constant for ideal gas. So these are the result we derived only from these two arguments, right? So let's get into more detail of this thing. So what idea is that I have this function which I'm interested in evaluating more, not only having these simple arguments, but I want a bit more detail. So and I'm rewriting this same function like this. So n I'm putting in subscript and I'm putting e star. If you remember my e star, if I see that my e star was yeah, I should have it somewhere here, right? So this E star has E and V inbuilt. So it means my this E and V functionality is inbuilt in E star. So it means I can just simplify for just for simplification, right? Instead of every time writing this NVE a long expression, I'm just jumping to this simple you can say sample. Okay. Now if you see our equation earlier, so we have this kind of equation, right? So nx square, ny square, and z square. So single particle energy eigenvalues. We saw this relation, and you also know that equation of sphere is written something like this, right? X square plus y square plus z square equals to r square, where r is the radius of your sphere. So here I try to actually, this is something not available in your book. So try to understand. So this will recorded lecture as well as these notes will be with you, but try to understand and try to ask the question that how it happened. Okay. So my point is, so if I try to draw a sphere in 3 dimension, now try to see here I am talking about one particle, right? And my sphere is in 3D. My sphere, this is in 3D. Okay, so I'm drawing this sphere. So my axes, I'm just labeling them with nx, ny, and nz. Okay, so and what's the radius of this sphere? So the radius of this sphere, I'm taking it to be square root of my this epsilon star. If you just compare these guys, right? Now, the question we are interested in answering is that how many possible number of microstates are there if I give you this geometry. So what's the fun to map this relation similar to that of a sphere, right? As I mentioned earlier also, so you can make a table that what is nx, ny, nz is. So you can have different values, 111, 112, and so on, right? So actually there are infinite number of such possibilities, but it is going to be constrained if I fix the E star, right? So it means that's why this sphere has certain radius, which is dictated like this. Now the idea is only certain specific values are allowed, right? So like my in real 3D space, my XYZ, it can take any real positive and negative value. But for this sphere, only allowed values are positive integers. So mind it, right? It's written here. Only positive integers are allowed. So if you see, only 1/8 of the volume of this sphere is going to contribute towards the number of microstates, because only in this octant, or I would say as you call in your two-dimensional quadrant. So here we have 8 equal parts, so it's a octant where my this condition is going to be satisfied, that my nx, ny, and nz, they all are positive. So this is the positive octant actually. Okay, so the number of microstates accessible to one particle, again I'm putting one here. Okay, this is exactly equal to the number of lattice points. Again I am saying only positive integers are allowed on the surface of a three-dimensional sphere with radius square root epsilon star, only on the surface, right? And why this is important point, why I'm calling this as lattice point. This is something I would give you guys to think about. Okay, so this I put as a kind of homework, do it yourself. Why lattice point? Why not every point is available? Like for example, I would say only this point is available, this point is available, this point is available, but no in between thing is allowed. Why so? Okay, just think and try to answer me, or in WhatsApp group, or maybe via mail, or maybe in next class. Okay, try to figure out why only lattice points is so important. And the positive integral, I think you understood. Okay, so if I count these number of points, so they are basically my available number of states, right? So similarly, if I extend this argument to n particles, right, now this you have to like wrap your head around that for n particle, my this number is going to be again a positive integral lattice points on a 3n dimensional sphere. Now this is something which you may have to extend your imagination. So it's not no more a three-dimensional sphere, it's 3n dimensional, because we are talking about n particles now, right? Of radius capital E star square, right? Because if you remember, my E star was energy or scaled up energy for single particle, and then we jump to n particle. So I replace this with this thing. So it means my this omega n E star is going to be all these number of lattice points. Now it's the headache for us to calculate how many number of particles they will be. Okay, there is actually easy way to do this, although it appear hard, but it is not. Of radius this much. Let's see how we can do this. Any question till now before I move ahead? Now we are less or more near completion of this thing. Only certain some argument are required to be discussed. Less or more we are done. Okay, so now there are a couple of things, as I said earlier also, that this number as such, it's quite sensitive to this energy. In fact, this E has a E v raised to power 2 by 3 in it. Okay, so this is very sensitive. I mean to say, why? What do you mean by sensitivity? Is that if you change this energy even very slightly, this number changes very abruptly. Okay, so how you can see this? Actually, there are a couple of references given in your textbook. I just mentioned somewhere that you have to read this thing yourself also. That they gave basically kind of table that if energy varies like this, that how my number of microstates are going to vary. So this is very sensitive to this value of this E. But you know that my S is equals to K log omega, and this can be inverted to, and this also as a function of N, V, and E, and which I many times told that it can be in fact inverted to find energy expression, which is E is equals to E N V S, right? So if omega is fluctuating too much, which means entropy is going to also fluctuate. So if entropy is fluctuating too much, then it means my this energy of the system is going to fluctuate, but I need a precise or smooth value for this energy. Okay, and for that reason I won't be considering this omega to be what I would say the number of microstates. I would instead evaluate not only the number of lattice point on the surface of 3n dimensional sphere of radius square root E star, but instead I will calculate all the number of lattice point on the surface of radius square root E star, as well as number of microstates or number of lattice points within the radius of square root E star, right? So this is being written or discussed here. So instead of doing calculating this, and why we are doing this, I will tell you. Okay, so I'm just summing over all the energies E star. This is basically written E star dash, which are less than some E dash. Okay, so I'm going to evaluate all such energies, these all microstates within that 3n dimensional sphere of radius square root E star, and this sum I am going to symbolize with this new symbol. Mind it, this sigma n is not a summation. Okay, this is sample for number of microstates which are like expressed like this. So instead of omega, now I am going to jump to sigma, this new parameter, right? So instead of these old number of abruptly fluctuating number of microstates with energy, I am going to deal with this, which is a relatively smooth function of energy. And to see this behavior, there is a plot, I think figure 1.2 in your book. I'm not that much interested in discussing that right now. That is going to take a lot of time, because that's a basically a research article based discussion, right? So we can discuss that in maybe some additional time also, but here I'm not interested in doing this. But motive is fluctuation of this guy is large, so we are going to just smooth out its behavior by jumping to a new parameter. So the idea behind this, whole of the thermodynamic the dynamics generated by this omega is exactly reproducible by this, but with much lower fluctuations. Okay, so yeah, this is again written same thing but with full functionality. Okay, so I'm going to evaluate these for all the energies lesser than some upper bound. Yeah, this is what I said. Thermodynamics is generated by both of them is exactly same. So this is what I was saying. You are supposed to self read this. I'm not going to do this. Okay, it's figure 1 by 2 in your textbook. Okay, so let's see if we have achieved that much. So what we can do with this now? Okay, this is interesting result from your appendix and pure mathematics. I don't know if you are interested in doing such things or not. You know that if I, okay, let me quickly say this. Just a minute. So suppose I have a sphere in 3D, right? You know the volume of this three-dimensional sphere with radius r is something like this. It's 4 by 3 pi r cube, right? This is, I think, your sixth class result. And surface area of this three-dimensional sphere with radius r is 4 pi r square, right? So this is what you are comfortable with till now, right? But life is not going to be so simple. Now you are in masters. So what if I tell you that now you have a 3n dimensional sphere? So how you can write the expression for suppose n dimensional sphere with radius r, right? So there must be a way to do this, right? Surface area of n dimensional sphere with radius r, right? These are valid questions, right? So answer to these questions are very well explained on this page in the appendix of your textbook. I'm not going to do that again because this is pure mathematics and you can see it's, I think, hardly a couple of pages derivation, but I'm interested in these results. So volume of an n-dimensional sphere with radius r is just pi n by 2. You can see n by 2 factorial is important here, r raised to power n, and you can put this n is equals to I would say uh, uh, the real space dimension so that you can see how these are going to reduce up to your um, normal three-dimensional space, right? So yeah, so this is basically 3 for three-dimensional space. Then this will be pi raised to power 3 by 2 r raised to power cube, and then you have 3 by 2 factorial, right? And 3 by 2 factorial you can simplify to the real numbers via gamma function actually. Okay, so this will be 3 by 2 into 1 by 2 of gamma function, and I think gamma function is square root pi if I remember. So that's how it comes out to be 3 by 2 kind of thing. So you have to see this, even I don't remember this exactly. Okay, so now why I want to use this, and similarly surface area is also written there. You can see that appendix, but I am not interested in this derivation right now. So let's see, because I am interested in the volume of octant in 3 n-dimensional space with radius square root e star, right? So you can very easily see that such volume will go something like this. So pi raised to power 3 by n by 2, because now my n is 3n here, right? For this formula you can easily see. So this is going like this: 3n by 2, 3n by 2 factorial e star raised to power 3n by 2, because if you remember, this is my radius for my ideal gas situation, square root of e star. So here radius power n, but because of this square root, so this 3n by 2 comes. Okay, now again for this three-dimensional sphere we only took 1/8 of the volume, right? 1/8 is because we were in 3D, so it's basically 3 raised to 3 1 by 2 raised to power 3. So we divided our full volume by this, because only positive octant was you can say contributing. But now similarly, if we are interested in 3n dimensional sphere, so we have to divide our full volume, which is somewhere here like this: 1 by 2 raised to power 3n, because we are only interested in the positive nr values. Okay, so you have to divide this by this number, so you are going to get the number of microstate, something like this. So these are the total number of microstate. I think you can appreciate that how this has been derived. Okay, so not hard, very hard to see. And now we know that we have our E star in terms of E also, right? So if you use that equation, I think equation number 8 on I think 3 slides back, so then you can use that E star, put that here, you will get this result. I'm not much interested in mathematics, but I am interested more in what are the crucial points, because this is algebra, you can do, it's not very hard. Okay, and again because we know that entropy is going to be log sigma, so we are going to take log of this number, so just take log here and log of this whole bracket, right? And you know, you might be aware about this Stirling formula. If n is very large, so your log n factorial is n log n minus n. Okay, so you can see actually plot of this, how much deviation is there for lower n's and large n, because here my number of particles are quite large uh, for a macroscopic system, so this I can apply comfortably, and that's why I'm most of the time I'm using this approximate equal to signs, right? So because these are approximation, so if you just do this, so then equation 17 reduces to this kind of thing, right? So this n which was appearing here in power, this will come in front, and yeah, so then this 3 by 3 and by 2 in the denominator, it goes on another side, because it was factorial, and using this Stirling formula you will have 3 by 2 n kind of thing. Okay, rest of the terms are absorbed with this. So this is a kind of a relation which we see, and just multiplying this by k is going to be your entropy. That's nothing more to that. Okay, and I know we are a couple of minutes above our time, so I think I can stop here. Yeah, so let's stop here. So from this equation we'll continue next time. Okay, and if you have any question, please type in, or otherwise you are good to go. Thank you. So either ask your queries, or you may leave the class. You're welcome, Saubhagya.